Hi, how are you? Can you hear me well?
Yes.
Let me introduce the today's speaker, Dr. Bhargav Vaidya. Friends, Dr. Bhargav Vaidya is an associate professor in the discipline of astronomy, astrophysics, and space engineering at the Indian Institute of Technology, Indore. He earned his PhD from Max Planck Institute of Astronomy in Heidelberg, Germany in 2011. Special focus of this was on theory of disk and outflows around young massive stellar objects. Following his doctorate, Dr. Vaidya pursued postdoctoral research at the University of Leeds, UK, and University of Torino, Italy, in 2017. Then he joined IIT-Indore. He is currently leading a partner group with the Max Planck Institute of Astronomy, focusing on simulating active galactic nucleus. We call it the AGN, particularly the jets in the era of multi-passenger astronomy. Dr. Vaidya's research interest encompasses computational astrophysics, magnetohydrodynamics, and radiative transfer. He specializes in studying astrophysical and space plasma flows through numerical simulations, with particular emphasis on AGN jets, space weather modeling, and the interplay of shocks turbulence and particle accelerator focusing in astrophysical and heliospheric environment. He is a co-developer of widely used astrophysics code Pluto and has contributed to the development of its hybrid simulation capabilities. Friends, he also will be talking about SEDs, and these SEDs maybe which is called as spectral energy distribution with a live demonstration. I welcome sir on behalf of Wilson College and IIT Mumbai chapter as well as the Krittika to this session and request you to start your presentation.
Great. Thank you, Professor Bhole and Professor Shetty for a very, very kind invitation. And also to the IAPT team and the Kritika team at IIT Bombay. I know the team is extremely active in doing a lot of outreach activity. And this is indeed a very, very special thing where you actually train so many of students. I can see almost 175 participants are online now on Python data analysis. So now, since it's a completely online platform, what I would really let me put extremely clear the ground rules that let it be extremely informal. And I would request people who have doubts at any point to please raise their hands, and then I would request the moderator to please unmute them so that they can ask their questions immediately. I don't mind getting interrupted in between. So please, if you have any questions, feel free to ask, and that would actually make the whole interaction much more easier. Now, as Professor Bhole rightly mentioned, that I will be focusing mostly on analyzing jets from active galactic nuclei. So what I'm going to do is initial 30 to 40 minutes, I'm going to start with an overview of what I want to do, what are all the terms and conditions and all the terminologies that you encounter in AGN jets, especially for people who are new to this topic. I just want to put them on the same frame, considering that you have a bachelor's or let's say pre-master's curriculum background. And then I have already shared the Google Drive link with some IPython notebooks. And so we will go through those IPython notebooks. And at the end of each IPython notebook, there are some tasks which I would encourage all of you to do and perhaps submit at a later stage for whatever, if you want to get more interesting aspects of it. So let me first try to share my screen. So let me share the entire screen. If I can Screen. Yes. Um, can you see my screen, everyone? Anyone can just please
Yes, sir.
erase.
Yes, sir.
Great, great, fantastic. Thank you so much. And let me just make it full screen now. So it's perfectly full screen now. All okay?
Yes, sir. Yes, sir. It is visible.
Fantastic. Okay, great. So let's begin then. This is the last day of 2024. While we celebrate the new year by putting jets and rockets up in the sky, today let's basically begin by learning jets which comes from the black holes. Now, these jets, you can see a very nice image in the background. It has some very colorful stuff. Of course, stars are all around the foreground, background stars. But what is focus over here is basically this beautiful pink color structure that comes out from this central region, which is white in color. And it is a beautiful pencil beam-like structure coming up and forming these very strong kind of bright regions here, which are essentially known as the hotspots, and the very beautiful expanded pink structure, which is essentially called the radio lobes. And why it is called radio lobes? Because the emission that you get is basically in radio band, which has been detected. And on top of that, you basically see some blue diffuse emission, and that is mainly coming from the hot gas that surrounds this particular region. So I see a chart. Okay, radio jets. Yes, that's correct. So that's basically what you see here. And the idea over here is that we would like to understand how these jets evolve, how these jets basically emit, and how do you basically study the properties of these jets as we go along, right? So that's the idea behind today's exercise as part of the school. So in the next 2 hours, of course, we cannot cover everything in detail, in depth, but I just want to basically give you an uh, kind of a kind of a taste to what people actually do when they do modeling of AGN jets. Okay, so this is something which is like the tip of an iceberg, but I would really request every one of you to go deeper into this and get more and more insight with the tool that we will be learning today. And that is essentially the highlight of this lecture. Essentially, if you look at galaxies, right? I mean, saying galaxies are essentially collection of stars surrounded by dark matter halo. And you can see the typical sizes are of the order of kiloparsec scales. And the idea is that they can be distinguished in two classes in general. One class is essentially known as the normal galaxies, or essentially is where you basically can see on the left hand side, you have a beautiful spiral galaxy which you're looking from the top. And you can see there's a central bright region where essentially the hot gases and where you have the black holes at the center. And then surrounding are these beautiful stars and these dark features, which are essentially known as the dust lakes, or where you basically form newer stars over there. And what you essentially have is most of the emission or most of the light that comes out from these galaxies is essentially dominated by the starlight. So the light coming from the stars. There is one thing which has to be known a priori in astronomy, that any object that you study in astronomy, you cannot basically go there and measure by scale or anything like that. Okay. So the way to basically do any estimation of astronomical objects is via the photons of different wavelength that you receive from them, and that's the only way you can analyze them. And this is the basic idea behind what today's exercise is all about, where we will kind of analyze the photons that come from these astrophysical objects, specifically the AGN jets, and try to understand that can we actually can we estimate certain dynamical parameters of these jets. Let's say its velocity, its all these aspects, and so on. So as it is, as you can see that most of the emission is coming from these star-like objects, which are very much present all over the galaxy. And these normal galaxies have a very weak accretion rate. By accretion rate means it's the amount of material getting accreted onto the central object. How much faster the material is accreting into the central object it is much, much slower, relatively slower, and it does not have any prominent outflow or jet which is perpendicular to the black hole or the plane in which you are basically seeing this. This is a normal galaxy. But if you look at an active galaxy, the active galaxies are very interesting because on the right hand side, you can see a very nice active galaxy. Now you are seeing the galaxy edge on. Inside the galaxy, you still see these dark lanes, which are, these are optical images, by the way. You can basically see these dark features also over here. This is where new stars are formed. There are, of course, stars present here at the center, which are highly forming stars and so on and so forth. But what is dominated in these kind of, what the emission, dominated emission, is what comes from these jets, and they are known as non-thermal emission. Now, I will explain to you what are non-thermal emission, because that is very, very important and crucial for today's exercise. Okay. So, as you can guess, non-thermal means not thermal, of course. So, what is essentially non-thermal? We will come to this, and most importantly, these active galaxies have a presence of a prominent jet. The jet are nothing but fast collimated beam of plasma that is ejected in a direction perpendicular to the plane of the galaxy, and mostly they are kind of originating from the central black hole that lies at the center of the galaxy. So now the question is whether these jets are common only to AGNs. Well, no. Jets are pretty much everywhere in astrophysical environments. Now, this is the top image that you see. Can anyone tell me what is this top image? From where this top image could be taken? Anyone has any idea? Anyone, maybe chat may could be also. Yeah, sun, exactly, sun, exactly. So there are people have put sun. Now, this is exactly our sun, and you basically can see, yeah, there is a hand raised. Swam, do you want to have a question? Do you have a question?
Sir, I was answering the question. That's why I.
Okay, great. Fine, no problem. Yeah, okay. So this is basically the sun, and you can basically see a plasma which is by launched perpendicular in this direction. And here, most of the plasma is kind of attached to the magnetic fields from where it is kind of getting launched. So this is basically known as solar jets, and you can clearly see in different wavelengths, which is written over here. AIA 304 is 304 Armstrong, 171 Armstrong, 335 Armstrong, which basically cater to or are sensitive to different temperature regions inside the sun. And thereby they show different signatures, or in this case, quite similar signatures, but in general, they can cater to different heights above the photosphere of the sun. And that gives rise to these kind of jet features that you essentially see. What you see on the left-hand side, bottom, are basically stellar jets coming from young stars. And these are essentially molecular emissions. So this is shocked H2 and molecular emissions, which are essentially being seen here. And you can beautifully see how the jet is kind of coming from this inner region, originating where the star is formed, and it is kind of penetrating outwards from this very beautiful region coming out from there. And these jets are also common in not only singular stellar objects, but multi-stellar objects also, the binary stars. For example, if you have a companion massive star and a white dwarf or a black hole or a neutron star at this thing, you basically can have material being accreted, and you can essentially throw out stellar mass. If you have a stellar mass black hole also, you can basically throw out jets, which are known as microquasars. And also, if you basically have a massive star kind of collapsing and forming this thing, then you essentially also form gamma ray burst. Yes, Rajeshwaran, question please.
There's a hand raised from Rajeshwaran.
Sir, how can I distinguish between a quasar and active galactic nuclei? Are both same or different?
Sorry, how do you distinguish between?
A quasar and active galactic nuclei, sir.
Oh, well, quasar and active galactic nuclei are the same. I'll come to that part. So essentially, these are quasi-stellar objects. So they are far off these things, and they are kind of that type of active galactic nuclei. Okay, we'll come to that distinction also, and that I'll come to this. Definitely come to this. Swayam, you have a question?
Swayam Dubey.
Sir, if nothing can escape the black hole, then how these jets are escaping the black hole and
Very
are
nice question. So basically, they are actually launched from a region surrounding the black hole. Okay, so basically, the material surrounding the black hole, nothing can escape the event horizon of the black hole. Okay, so if the material is coming from the close by region, once I show you the image, then in the next slides, it will be more clear how these things are essentially launched or how they are essentially produced. So I'll come to all of those questions. So just keep it right now at the end of this talk so that if you have further questions, we can take it up at the end of the talk because then it's easier for everyone to kind of pay attention. Now, when you look at these jets, so this is basically typical of all the different kinds of jets that we see. But if you look at, let us focus now on AGN jets, so jets which are essentially coming from supermassive black holes. Now, when you look at these AGN jets that come from this very supermassive black holes, if you look at a very large scales, so these are like galaxy scales or more than galaxy scales or wider than galaxy scales, you can basically see that it has a very chaotic signature. So what you see over here is the same jet, It's M87 galaxy. This is, I'm sure you must have heard about this because of its famous picture of the black hole from the Event Horizon Telescope. But M87 jet, if you look at on a much larger scales, this is how it looks like. And it is in radio image. Over here, you can see how chaotic this whole thing is all about. But you still see signatures of some longitudinal flows, which are essentially coming from the central part of the galaxy. And these are essentially like the jet features. But if you zoom in to this little red region that you see here, you can very nicely see the beautiful collimated jet feature, which is coming. But this collimated jet feature is not a cylindrical thing. It is kind of like wiggling. Just like you basically light an incense, agarbatti stick in your home doing puja, you can basically see that the agarbatti smoke also wiggles as around. So it is exactly doing a very similar kind of thing. And if you go more deeper, more closer and closer and zoom in, you can see several structures that are appearing in these jets. So the jets, what you can see over here are not some beautiful cylindrical shaped features, which are like boring, but it are very interesting from the perspective of the fact that it has all sorts of funny things that is basically happening over there, all sorts of interactions that is happening over here. You have a much more parabolic funnel-shaped jets. You have turbulence. You have some mixing of material happening. Sometimes you can see formation of knots, which are like bright features which exist within these jets. And very importantly, which is one of the most interesting aspects of these AGN jets, if you look at this second image, you can see that the jet is only in one direction. And the other direction, you don't see the jet, but you see some feature at a very far off distance from this jet. So this is an extremely important finding where you have only one-sided jet. And it is not because you have some material around it so that you cannot see the other side of the jet. It is a physical effect. It's called relativistic boosting because these kind of jets are this such feature where you see only one-sided jet and not the other side indicates that these jets are relativistic in nature. And indeed, these jets move with speeds very close to the speed of light. So they have special relativity in play as they go along. And then, as we will see later on as part of the talk, we have relativistic Doppler effect, which gives rise to the boosting. So the jet that is coming towards you is boosted in the emission of jet coming towards you is boosted. And so you only see one side of the jet, whereas the jet going on the other side is de-boosted. And therefore, you don't see the other side of the jet. So it's an actual physical effect because of relativity and not because some material is kind of shrouding or blocking our view. So this is a very important aspect here as far as this thing is concerned. Now, coming to what was asked, whether how the material basically can escape the strong gravitational potential of the black hole, that we know that even light cannot escape. But that is only possible within this little event horizon where nothing can escape. But all this material that is kind of thrown into these relativistic jets is basically coming from the surrounding material, which is kind of pushed in the longitudinal direction via magnetic fields. Now, magnetic fields are one of the most important aspects of AGN jet physics, and where you can basically see that how the material from the larger region of the galaxy is kind of dragged inside to the central black hole and is kind of pushed in a direction perpendicular because of rotation in the disk, because the disk is rotating, and the magnetic fields, which kind of provides a funnel-like structure for these jets to basically escape these things. So within this event horizon, yeah, nothing. We cannot see anything. But if you look at this image, which was basically obtained by the Event Horizon Telescope, you can clearly see that all the interesting photon ring, there are many aspects. There's an event horizon, there's a photon ring, and so on and so forth. But the material we can see swirling around and basically is showcasing how the material is kind of getting accreted onto a black hole. At the same time, you see formation of these jets, while the material from the accretion flow is converted into the upward direction. So there is a lot of details here, but I cannot basically go in all the details in this little talk. I want to just focus on what sort of radiation mainly comes out from these galaxies. But there's a whole new physics if you want to understand how jets are launched and so on. But just to summarize and to make a comparison, because this kind of, it's always good to have some idea of numbers when you are basically looking at these jets. So if you look at AGN jets, they typically are of the order of megaparsec scale. So one parsec is of the order of 10 to the power 18 centimeters. Okay, so it's all 1 megaparsec is of the order of 10 to the power 20, 18 plus 6 is 24 centimeters, right? Whereas young stellar jets are only few parsec jets. Okay, so that's not very much in size. So AGN jets are much larger. They are like peas in the sky. Again, the velocities typically are relativistic in nature by the fact that we saw that it is one-sided, whereas young stellar jets typically have maximum velocity of 500 kilometers per second. It's just barely supersonic. Yes.
Sir, actually, in the initial time, means during the starting, you told us that there are some galaxies where these jets occur, and in some galaxies like ours, it doesn't occur. So, means what are the conditions that enforces the material from the outer space to come and get condensed and then launched in the perpendicular side? Means why doesn't occur in our galaxy?
Very important point. So if you go back to my earlier. Come on. So basically, the most important aspect is that there is a very weak accretion rate. See, you can basically throw the material upwards if you have material to throw upwards. Okay. If your material is not coming or is not being fed at a rate, you cannot produce continuous outflow at in form of a jet. That is point number one. Point number two is that you need to have accumulation of magnetic fields which basically funnel this outflow in the perpendicular directions, and you should have a decent amount of rotation over there, continuous disk kind of structure, basically forming there so as to kind of form the base or the platform from where the jet submerge. Okay, so these three important aspects are crucial for deciding whether a galaxy can have a jet or not a jet. Okay, so our galaxy Milky Way, for example, does not have very strong accretion rate. Our material is not getting accreted at a very fast rate as expected for an active galaxy. That's why they are called active galaxies, because they're actively accreting material and they've been launched because of the magnetic fields. You understand?
Okay, sir.
Right. So now, right. So basically, that's the idea. And most importantly, AGN jets have very low densities, whereas young stellar jets are high dense. They are highly dense, and they are even denser than the ambient medium. And because they are low density, it's easier for them to basically throw at relativistic speeds. You need less power. You don't need tremendous amount of power to do this. AGN jets are hotter, extremely hot. They are of the order of 10 to the power 7, 10 to the power 8 Kelvin. Whereas so hotter than the ambient. The ambient temperatures are not that high. Whereas the stellar jets are colder than the ambient. ambient material is much hotter, and the jet itself is much colder because they are denser. Okay, and typical magnetic fields are present both in stellar jets and HN jets because without magnetic fields there are no jets basically. So magnetic fields are extremely important, and they range from few milligauss to microgauss in both cases. Yes, yes, Palusha, please go ahead. Yes, Palusha, go ahead.
Hello, sir.
Nivedita, sorry, Nivedita, yeah.
Hello, sir. Good morning, sir. Sir, you have said that the role of magnetic field is very important in the jet formation. So, does the minimum magnetic field required for a jet to form, would it differ depending on the mass of the black hole, or what it actually depends on, or is there a
Yeah, it's a
minimum?
very interesting question. Actually, the point is that there are several mechanisms to explain how the magnetic fields come into place to begin with, right? I mean, you should basically ask the question, why would the magnetic field comes there, right? I mean, what takes the matter? So basically, one of the arguments is that these magnetic fields is kind of already inherently in very weak values, inherent in these gas, which is basically getting influenced. And because these gas are hot, you essentially drag the magnetic field lines along with them. Okay. So that's the idea behind this whole aspect. One idea behind how these magnetic fields get accumulated. Certain times you essentially have very weak magnetic fields already present in these accretion disks, and that is kind of dragged along and channelized. So there are several simulations and several models to explain how the magnetic fields essentially come so close to the black hole in order for the jets to get launched. Now, as far as the threshold magnetic field is concerned, of course, it has been known very well that these jets very close to the black holes are magnetically dominant, meaning if you basically have energy partition, as we will see in our analysis also. So, for example, there are several energies, right? The jet will have kinetic energy because it's at some velocity. It will have magnetic energy because it has magnetic fields. It is hot. It has thermal energy. Now, if you basically say that, okay, is kinetic energy greater than magnetic energy, thermal energy, or what is dominating? Then close to the black hole, you see that it is dominated by the magnetic energy. But as it moves along, what happens is the magnetic energy gets decayed or dissipated. And ultimately it becomes kinetically down. Okay. So there are several aspects of jet physics is there. But again, if you want to go, then there will be like a full 2-hour lecture only on that. So let's basically focus on the different aspects of the jets and the radiation coming out of this. But I would be more than happy to take on a separate day, a complete lecture on jet physics or jet formation and so on. So, okay. Now, coming to this slide over here, which kind of showcases what actually the jet looks like. I mean, what is a real kind of a cartoon picture of how the jet basically, or the jets, or the flow around the galaxy or the black hole is about. Now, if you look at this, at the central, there's a black hemisphere object, is a black hole. You have a jet that is coming out in light blue color, triangular collimated things. And then surrounding that thing is a very flat orange kind of structure, which is known as the accretion disk. And connected to the accretion disk is a big donut-shaped structure, which is called the torus. Now, on top of these black holes, you essentially you have these light blue color clouds, which are essentially known as broad line regions. Why they're called broad line regions? Because they move very fast around the black holes, and they are mostly believed to be some fragments coming from the torus, some fragments coming from the disk, and they are just kind of caught in the gravity of the black hole, and they are moving very fast. Okay, and as you go above and above, there are also like other clouds which are known as narrow line regions. They are kind of, since they are much away from the black hole, they move pretty slowly. But what is important is that this jet, when it is moving from the black hole, starting from the black hole, interacts with all of these things as it goes out of this whole thing coming out over here. Okay. And now, depending on how you are looking at the jet, because it's not always that the galaxy will be pointing towards you or pointing away from you or at a perpendicular, they can be randomly oriented. So depending on the viewing angle of the jet, one can basically distinguish this jets or this whole picture in different categories. In case where the jet is directly pointing towards us, just like a flashlight coming towards on your head and on Earth, then such kind of jets are known as blazars. And we will study one such blazer today. And why they are important is because since they are like, you can see that they are hollow structures, funnel-like structures. With blazars, you can really penetrate deeper and understand what is happening closer to the black hole. Because everything is coming in on your face, so you can basically look inside what is basically happening. If you look at from certain sideways part, you see this is a radio loud quasar. Then you have a broad line quasar, a broad line radio galaxy. So this is mainly coming from the broad line region, narrow line region. So on the top of this dashed line or dotted line, these are radio loud because most of the jet emission, as we will see, are in radio band and then all the electromagnetic band. And if you don't see the jet, let's say from the other side, because of boosting or so on, then they are called radio quiet region. And in that case, you basically have a very bright central object, then it is called a radio quiet quasar. But if you basically see a bright central object with a jet, that's called a radio loud quasar. So again, the person who asked about quasar and AGN, quasar is a type of AGN. It basically just looks not directly into the jet, but at a different angle with respect to that. And in quasar also, there are two types, radio loud and radio quiet, depending on whether they are emitting jets or not emitting jets. Okay, so that's the idea behind radio loud and radio quiet. And of course, CFAT 1 and CFAT 2 are also there. So now, what our task today will be that this cartoon picture is there. That's nice. But how do you know that this cartoon picture is real? I mean, how do you, people have written out papers and written on models, but how do they even know this? Right? I mean, is it based on some random dream or random guess? No, of course not. It depends on how you analyze the photons that are coming from this jets, and how do you analyze, looking at that photons, how do you make an interpretation of these AGN jets? So that is the crucial aspect that we're going to study, and that is basically the part that I want to cover as part of this this tutorial today. Now, everyone I'm sure is well aware of this electromagnetic spectrum, and the beauty is that AGN jets emit in the full electromagnetic spectrum, complete, right from radio up to gamma rays. In all bands, AGN jets emit. Okay, so that's the beauty about it. Yes, Draksha, please go ahead.
Sir, could you please go back to the earlier slide?
Sorry, should I go back to?
The previous slide.
Sure, I can.
Yeah, so in this picture, there is only one jet coming from this black hole.
Yeah.
Why is this so? Like you mentioned earlier, because of the relativity.
No, I mean this is Draksha. This is more like a cartoon picture because you also want to show the radio quiet part. Okay, in general, jets will come out. They are bidirectional. Okay.
Yeah.
Now, in general, they are bidirectional, but since they wanted to show in the cartoon the radio loud and radio quiet together, they have preferentially put the jet in only one direction. Okay, so this is a cartoon picture, just to demonstrate all the aspects. In reality, the jets are always bidirectional. Okay, but as I mentioned, that in AGN jets, since they are relativistic in nature, sometimes you do not see the backside of it. And that is mainly related to the fact that your jet that is coming towards you is boosted. We will see what is Doppler boosting. Okay, so that is.
Yes, sir. Thank you so much.
Right. So basically, when you look at an electromagnetic spectrum, it covers a huge band in frequency, in wavelength, whatever way you want to learn or perceive it. But what is important is that AGN emits in essentially all bands. Now, how does the emission that comes from the AGN looks like? Now, this is something which you are well aware of, looking at our sun. Now, our sun, we all know, I'm sure you have also done a stellar tutorial earlier, is essentially a black body. Okay, So if you look at a black body spectrum, a black body spectrum basically is something like this, where you have irradiance, this watt per meter square, that is the energy emitted per unit time, per unit area, per unit wavelength or frequency is shown on the y-axis, and the wavelength in nanometer is shown in the x-axis. So here you look at the sun's spectrum. So this is basically what is the spectral energy distribution. It is nothing but how much energy is coming in each wavelength band. Can I request to please mute? Yeah, great. So how much energy is essentially coming in each wavelength band is what, and if you make a histogram of this, so you basically say that, okay, I have a filter at 240 nanometer, at 500 nanometer, 750 nanometer, and so on. And in each of this bucket, I'm collecting the photons of those particular width. And then I've made a histogram of that thing. That essentially basically is nothing but a spectral energy distribution. Now, in this case, it's a black body spectrum. And I'm sure you are well aware that the peak of the black body spectrum, or the peak wavelength of the black body spectrum, times the temperature is essentially a constant for the Wien's displacement law. And what it means is that if I change the temperature of the object, let's say instead of sun, I put a massive star, I hope that you are aware that the black body spectrum changes. Okay, so the spectrum changes by changing the temperature. And therefore, the radiance or the irradiance or the emissivity or the flux, whatever it is, that is emitted out from the black body depends on the temperature. For emissions where the emissivity or the flux or the irradiance or whatever, the energy emitted or the power emitted or the luminosity emitted by the body depends on the temperature, those kind of radiation are called thermal radiation, because they depend on the temperature. Okay. But then, of course, if they're thermal radiation, then there must be non-thermal. Now, non-thermal radiation are a class of radiation where the emissivity or the flux has no whatsoever relation with temperature. They don't depend on temperature at all. Okay. And that is exactly when you do an SED measurement of a typical active galactic nuclei, you see a classical non-thermal radiation signal. Now, how do we know this? We'll come to this. Yeah, Weber. Question. Weber?
Mr. Vaibhav.
Yes.
Hello, sir.
Yeah.
Sir,
Weber.
how one can measure the flux and variability density of a blazar using
By just putting in different kinds of telescopes. And that's exactly what we will basically do. We will use the data of different telescopes in different bands and looking at the blazar. So essentially what you're doing is, telescope is nothing but a bucket. Okay. You are essentially collecting photons in different wave bands. And the number of photons collected per unit area is essentially nothing but the flux. Right? Of course, you are categorizing in energy. So that's basically the whole idea behind collecting photons from different wave bands. So that's what you do. From blazar also, this jet that is coming, even though on your face or towards the observer, emits, right? It is basically all sorts of emission mechanisms happen there. And as we will see that it emits it in different processes, and that's basically the idea that we see. Okay, so I just want to highlight over here that there are very characteristic signature spectral energy distribution of an AGN jet. As you can see, there are two classical humps. The first hump, which is, let's say, a low energy hump, which is on the left-hand side, shown with a dotted curve, and a high energy hump, which is shown with the solid line. Now, there are two different models here. Pink model, which is what we know as the leptonic model. And why we call it leptonic is because the emission that is coming is mainly governed by the electron which is present inside these jets. So the jet essentially is, as I said, a plasma. Plasma means it has electrons, protons, positrons. We really don't know that. Even if it has all these things, question is, what is dominating the radiation from these jets? So these pink lines are essentially indicating that both the low energy and the high energy are kind of dominated by electron processes which involves electrons. We'll come to which processes. And the hadronic one clearly showcases that there is some signature difference. But even in the hadronic one, the low energy part, which is the low energy, mainly comes from electron, but the high energy blue solid line comes from proton processes. Okay, so that's the difference between leptonic and hadronic in AGN jets. So now the whole research in this field is which mechanism dominates and for which sources and why. Okay, so that's not clear up till now, and people are still wondering, is there a way to kind of distinguish between these things? And as we will see, it is very difficult to do that. So just to give you an idea on what, before I go to leptonic and hadronic processes, let me give you an idea on what actually, if non-thermal radiation does not depend on temperature, then what does it depend on? So it depends on the particle energy distribution. That means you have a jet filled with particles. You can think of jet as filled with particles, electrons and protons, and electrons and protons will have itself an energy distribution. Say some sort of power law distribution or some sort of weird functional distribution, some relativistic Maxwellian distribution or whatever it can be. Or it basically has, let's say, a power law distribution. Then this power law distribution evolves within the jet due to several acceleration processes, because of magnetic fields, because the energy is lost, as we will see, and because you have surrounding photon fields, which kind of play a role in modifying the spectral energy distribution and so on and so forth. So on all these parameters, which we will use in our modeling to kind of showcase that all of these are important, and nowhere, absolutely nowhere, we will have temperature of the gas over there that determines the radiation. That's why these radiations are called non-thermal radiation. Okay. Now, to look at in a much more detailed manner, I don't want to go into very much detail, but at least to have a look at it, we will be focusing mostly for today's tutorial on the top left portion, where we will only do leptonic modeling. Now, that's why I want to spend a little bit time over there in leptonic modeling. So this is again a different way of representing leptonic and hadronic. And as I said, that there are two humps, very classical two hump signatures. This is a very typical spectral energy distribution of an AGN. And in leptonic emission, the low energy hump, that is the left hump, is due to synchrotron processes. Synchrotron processes is when you have electrons basically gyrating along the magnetic field. And as we know that any charged particle, either accelerated or deaccelerated, will emit radiation. And that radiation is essentially, if the electron is relativistic, it's called synchrotron radiation. If it is non-relativistic, it's called cyclotron. Okay, so that is essentially known as the electron synchrotron radiation. And in the high energy part, what you basically have is synchrotron self-compton. Now I come to that, what is synchrotron self-compton? I'll come to that part in a couple of slides. But this is, and here as you can see, all the processes are dominated by electrons, nothing else. And if you look at on the top right, you have an electron synchrotron still dominating the leptonic part. Always the low energy is usually leptonic, but the high energy mainly comes from photopion detection. So basically you have protons and you have other particle processes which kind of gives rise to pions, and those pions basically breaks up into gamma rays, and that's basically what gives rise to high energy in gamma ray emission. Whereas you can have proton synchrotron, because protons are also charged particles. They will also gyrate along the magnetic fields and emit radiation. So they emit at much higher energy. So then you can have proton, but this requires a very, very large magnetic fields. And then there are the exotic ones, which I don't want to go into details. But what is interesting is that there are certain cases where they have found neutrino emission. And that is only possible if you are doing hadronic processes. So the whole picture is quite open right now, and we really do not know. So here is what I was talking about, synchrotron emission, where you have charged particles moving along the magnetic fields, and the radiation is basically emitted out, and it's beamed and so on because of the relativistic motions. And that is essentially what we will be modeling as part of our exercise in today's section. But another aspect, which is where I come, and that's where we understand what are the surrounding aspects. This whole picture is basically what is known as the inverse component. Okay, so synchrotron is one part. It is fine. It's mainly coming because you have highly energetic electrons and they are gyrating along the magnetic fields. You have magnetic fields in the jet. You have electrons in the jet, which are highly, very, very highly relativistic, and they are gyrating and they are emitting synchrotron radiation. That's fine, easy. But then you have all sorts of photon field surrounding your black hole. You have photon field coming from the disk. You have photons coming from the disk scattering into this broad line region and giving you another photon field. You have the photon because of the synchrotron emission. Okay, so let's say a highly energetic electron gyrates along the magnetic field. A photon is emitted, which is a synchrotron photon, mostly in radio band, and it interacts with another electron. Okay, so this kind of thing is called synchrotron self-compton. So that is the synchrotron photon itself is basically behaving in an inverse Compton manner with a low energetic, high energetic electron interacting with low energetic photon, giving rise to high energetic photon and low energetic electron. So this is classic inverse Compton process. I will not go in any mathematical derivation here because that is beyond the scope, but we will be using the module which has all sorts of processes taken into account. And then you have external Compton, and if you are much further away, you have a very uniform global field, which is the cosmic microwave spectrum. So all sorts of processes come into play to determine the structure of the of these jets. And now, before we go into the analysis part, so before we really go into the analysis part, there is one little concept that I'm sure that you have heard and you have learned it, but it is also important to give you an insight into what this is all about. I'm sure you have all heard about Doppler effect. This is very simple school textbook problem. Like if I have a source or emitting a sound wave and then it is essentially moving, you can see that there will be a change in frequency or wavelength of the emitted sound wave because of the motion of the source or the receiver. Can happen either moving towards each other, moving away from each other, or one is stationary, one is moving towards, and so on and so forth. So all sorts of permutation and combinations are possible, mostly in longitudinal waves. Okay. Now, in general, we have a jet, which is so jet is basically, you can think of, as we will see in our model, we think of jet as nothing but a collection of blobs. Okay. So let us take one blob within this jet. And it's not necessary, okay, the blazer moves along your line of sight, but not all jet will move along your line of sight. So the jet can move in any particular direction. That blob can move in any particular direction with respect to an observer, that is you. Okay. So now what you have to do is something called as a transverse Doppler effect. And not only that, since this blob is moving with relativistic speeds, you will have to do relativistic transverse Doppler. And if you do the math, it's very simple. It's not that difficult. You can end up with this very nice formula, which basically relates the proper wavelength, that is the wavelength that is emitted in the source, to the observed wavelength, which is basically what we observe. In frequency, you can write it down like this, but essentially you have a Doppler factor which comes into play. Yes, Rajeshwar. Yes. Hello. Yes, go ahead. Yeah, Rajeshwar.
Sir, you continue.
Okay. Yeah, please. I think I'll continue. I think I'll continue because then we can take up more questions at it. Rajeshwar, we come to your question later. right? So now coming to the model that we will be basically doing, and we will be essentially um, uh, coding it in Python, is this whole idea about this zone. Please, I just have 2 slides. After that, we can ask all questions. So just let me finish these 2 slides, okay? So now our model is very simple. It's very straightforward. And we will apply this model to an actual observation of a blazar jet and try to see what properties we can determine of this blazar. Okay. So, and we will only restrict ourselves to leptonic emission for the time being for this tutorial. Now, for us, what we have is there is a black hole, there's a disk. Of course, there's a broad line region, narrow line region, as I saw. But what is interesting is that the region of the jet that is emitting, or called the emitting region, is a blob, a spherical blob of certain radius RB. And basically, it is emitting and it is moving with some Lorentz factor gamma. Lorentz factor gamma is basically nothing but 1 over square root of 1 minus beta squared, where beta is nothing but velocity of the blob divided by the speed of light. Okay. So this 1 divided by square root of 1 minus beta square is nothing but the bulk Lorentz factor gamma. Now that's basically the macroscopic picture. Now inside this blob, as I told you, jets are comprised of electrons and protons. There are electrons inside this blob which have a different particle distribution inside. Okay, so you can think of this that this blob is huge volume of mass. Inside this, there are hundreds and thousands and many electrons, and these electrons have some energy distribution among them. Now, given that and the magnetic field around that blob, how do the emission of this blob looks like? Now, that is what is the ultimate game or ultimate focus that we have to do. And what we have at our disposal is the choice of the properties of the blob, the properties of the spectral, the particle distribution, which is different than the photon distribution, the SED. The SED is the distribution of photons at different energies of the photons, but here you are talking about particle distribution, which is different. And then you have magnetic fields around it. And at what distance is our source? Because that is also important. If the source is very far off, the flux, of course, will be degraded by 1 by r square. That is very simple. Okay. So at what distance the source is? What is the property of this blob, with how fast it is moving, how much magnetized it is, what is the size of the blob? All these information we have, and at the same time we can also give information about how the particles are distributed in energy space inside this blob. Now, with all this information, what sort of emission such a blob can emit? And that is something which we have to figure it out. And for that purpose, there is a very nice tool written in Python, which is called AGNPy. And this is something which we'll be using as part of our tutorial and exercise to kind of study this, study these AGNs in details. Okay. So what we're going to do, this AGNPy is very comprehensive. It is a very full suite of all the things that I've discussed. But we will only synchrotron aspect and some self-compton. So that is basically, it is basically the photon that is coming because of gyration of electrons along the magnetic fields, and the synchrotron self-compton is inverse compton of those photon, which is low energy, with very highly energetic electrons. So when they kind of interact, they produce very high energetic photon in gamma rays. So that is synchrotron self-compton. So we will study this aspect and try to model our jets, a particular blazar, and see how all of these things happens. Okay, so this is the idea, and this is a tool which is freely available, open source. And I would request everyone, as mentioned in my abstract, you can easily download this with pip install AGNPy, and you can also have, because we have to do kind of modeling with an observation, I would also request you to install a package called Sherpa. SHERPA. I think all these details are given on the abstract itself. So these two modules are required along with the basic AstroPy, NumPy, which you would already have because of the earlier tutorial. Okay, so if you can install this too, and I can take up questions before I move on to the tutorial section. So this stops. I end here. As far as the initial aspect is concerned, you can ask me questions here, and then I'll move to tutorial. And I request everyone to please install AGN5 if they have not done yet, and SharePoint. Please go ahead. Questions.
Okay, I'll start questions. The first question is, where do these jets go? Or they wander in the space just like anything? Or can it disturb any star planet system?
Absolutely. Yes. So as I told you, the jets basically move right from the center of the black hole, crisscrossing the whole galaxy, and it can definitely have a significant impact on its surrounding material. It can impact the gas, it can heat up the gas, it can disperse the gas, and it can really have a significant impact. So this kind of processes are known as feedback. That is like the jet feedback onto the material through which it's passing through. So yes, they have a significant impact on the surrounding material. And they can really impact star formation in general. Star planetary interaction is very minimal for the jet signature. It's a very small length scales, but it can definitely impact star formation on much larger scales. Yeah, next.
Okay, the next question is, what is gravitational lensing?
Oh, okay. So gravitational lensing is very different than what I've been talking about. Gravitational lensing is that if I have a galaxy, let's say in front, and then there is a quasar at the back. Okay, so I am an observer. I have a gravitational, a very massive, what you can say, kind of massive object, a dark matter halo. Then the light that comes out from the background object gets bent because of the gravitational effects and the gravitational distortion, which is basically present. But it needs to have a massive things, and because of this, because of the bending of this light, you essentially see a more arc-like feature because it's not, even though it's a point source or even if it is an extended source, it will be sharp bend like an arc because it will kind of more certain aspects will get magnified, certain will be demagnified. So it's basically like this aspect of gravitational lensing. But it has nothing to do with the jets here, very different than, it has only to do with the lensed heavy object which is gravitationally heavy, and this in front of the jet at the back or the quasar at the back.
Yeah. While explaining the same, the question is, doesn't all this depend on the gravitational force of the black hole, hence the mass of the black hole?
See, basically, indeed, the accretion rate and mass of the black hole has a relation. But the point is that once the jet is escaping out, it is basically outside of its gravitational pull. Otherwise, it can never escape never escape to such large distance. So, in general, jet accretion, the material accretion is definitely related to the mass, which is there, the mass of the central black hole. But the jet outflow or the outflow rate in some way are kind of related, but it's really the jet is coming out of its the gravitational pull. So how far it goes and so on, that depends mainly on the magnetic energy, the kinetic energy with which the jet has kind of been powered. So indeed, the spin is also very important aspect. So along with mass, spin of the black hole is also very important for jet launching.
Yeah. The next question is, in the galactic evolution, what is the trend of jets of SMBH? I mean, our square A star is quite known, but was it always this way?
Well, look, if you want to ask me, I believe that all the black holes at some point were jetted. So they had jets at all point of time. But you see, what happens is that over a period of time, you can have depletion in star formation, depletion near near the black hole, and the accretion kind of stops or halts. Now, whether this is temporary, permanent, is yet to be seen. And it has a lot of impact, as you rightly mentioned, the galaxy evolution, like how the galaxy has evolved over the whole cosmic timescale. So whether that has been there now, in fact, JWST, if you know, JWST has been finding jets at redshift 7 Z8 galaxies. So this is like really very early in our cosmic timeline, and therefore jets are forming everywhere, essentially. So because it's very simple to form jets, right? You need mass accretion, strong mass accretion, magnetic fields, and plasma. That's it, and rotation. That's everywhere there. So why shouldn't it form jets?
Yeah. The next question is, are these AGN jets analogous to FRBs or are they completely different?
FRBs are completely different, essentially. AGN jets, FRBs are essentially fast radio bursts, mainly come from very highly, believed to come from highly magnetized regions or neutron stars, highly magnetized neutron stars. And that is mainly local, what you can say, some local influx of material or some kind of uh, material being injected onto the neutron star and giving rise to a sharp emission, which is like a fast radio burst. So this kind of aspect is still under debate of how FRB is essentially formed. But one popular model is that it is essentially magnetar, so very strong magnetic fields. But this has nothing to do with the jets. The jets are very, very collimated wave of plasma. So they are there. It is more localized kind of falling of material and so on and so forth. So that is very different than the jets.
Yeah. Next question by Kamal Raj is, what is the difference between blazar and quasar?
Oh, blazar and quasar, it's here, right? I mean, look, a blazar is a jet, an AGN jet, where you basically see along the line of sight the jet, and a quasar basically is what you see. Most of the emission. See, you are looking at a quasar in this direction. That means most of the emission is coming from the central black hole. Okay, so now the central black hole is very bright. So that's why when you look at the quasar, it's called quasi-stellar object. It's quasar meaning it's very bright central object. That's only what you see. But if you look at in radio band, you basically see a beautiful jet coming out of it nearby. So that is essentially quasar. But here, your jet is not along your line of sight. You are looking slightly off axis to the jet.
Yeah, with the same slide. Yeah, with the same slide, there is a question: what creates the magnetic field and what is its shape?
Well, the magnetic fields. It's a very difficult question. I mean, in universe, if you look at it, it's basically we still don't understand. There's a whole problem of magnetogenesis. So how do you generate magnetic fields to begin with? But we say that, okay, let's say there are weak magnetic fields. These weak magnetic fields tend to get accreted or get accumulated near the black holes because of the material getting them along. And then you form an hourglass shaped structure. So it's more like a parabolic funnel shaped structure through which these jets are essentially launched.
Yeah. The question is general: won't the fast-moving mass is in the periphery have charges, and if they move, won't they produce their own magnetic field too?
Yes, but usually these particles are the material is extremely less dense. Okay, so even though they are locally these little magnetic fields, but they are much lesser as compared to the global magnetic fields that are existing. Okay, so even these particles essentially move. They have their currents, but they are just like perturbations to the overall global magnetic fields, which are much larger in magnitude.
Okay. The next question is, the emission of jet from one side only will violate the momentum of conservation, right?
No, there is no one-sided jet. There are always two-sided jets.
Yes.
Always remember there are two-sided jets. There is no violation of momentum conservation. Unfortunately, not. So that's
the question is, can you explain pion delay and ICS?
Pion decay and?
Pion delay and ICS.
Well, I don't know much about this pion delay part, so I would not comment on it. But indeed, pions are essentially produced within these jets if we believe the hadronic scenario. But I don't know much about the pion delay and so on, so I cannot comment.
Yeah, with the same slide of leptonic hadronic, these conditions applicable to both leptonic hadronic in the same manner are different.
What conditions? I mean, the question is, see, leptonic and
Yeah.
So electronic is basically that all the emission comes from electron populations. That's the idea behind electronic. Okay, so all the dominant emission, like as I said, if you have electrons, so electronic is very simple scenario. So for example, you have these two humps. You have an electron, a magnetic fields, you have electrons gyrating. So you have synchrotron emission. So you have a synchrotron photon that is coming here. So basically, this is an electron gyrating along the magnetic fields. You have a synchrotron photon. Now, this photon will come out from this region, but you also have already other electrons, right? You also have very highly other energetic electrons. Now, this photon will come and hit an energetic electron. So essentially, what happens is that you have a high energetic electron which is moving, and then you have a low energy photon which has come out from the synchrotron process, and that interacts. And what happens is there is now an inelastic transfer. So inverse Compton transfer. So essentially, a high energetic photon is emitted out or scattered, and the energy is basically taken from the electron. So an electron basically reduces in energy. So low energy electron comes out. Okay, and this high energy photon basically goes in the second hump, because these are, if you have a radio and you have a very high energetic electron, it can give rise to gamma rays directly. So that is essentially, you have a population coming here in the high energy hub. So this is what is pure leptonic, because you don't need to invoke protons to produce this HA. They are known as leptonic. But if you cannot produce the high energy part, as we will see in our tutorial, that certain aspects, well, it's very difficult sometimes, then you need to invoke proton distribution. Then you have to say that, okay, there is proton somewhere. So then that becomes proton.
Yeah, the next general question is there. Elaborate on neutrino emission and
Nice.
discussing
So,
normal thermal radiation.
no, so so that's the beauty about AGN jets, that they are multi-messenger astronomers, multi-messenger astronomy. Now, multi-messenger astronomy is that how do you go beyond this electromagnetic spectrum, right? So this is the limit. I mean, from radio to gamma rays is the photons that are covering the whole band. Now, if you want to really understand even more, like for example, a neutrino emission is a deciding factor whether a jet is hadronic or leptonic. So that is very crucial to do this. So neutrino emission mainly comes from this whole idea about pion decay. So if neutrino is detected from a jet, then 101% it is basically hadronic. At least proton contribution is there. Now the question is, proton is being coming by interacting with the ambient, or it is inherent of the jet, is a question. So we don't know. So that is still a question, and people are still struggling to find answers to it.
Okay. Okay. The next question is asked by Tanisha. How do we understand the energy distribution of electrons and protons inside the block are present? The energy could potentially be very erratic as well, since everything around them, including the magnetic field, is changing erratically as well.
Yes, indeed. The energy distribution evolves significantly, but in general, basically, what you will see is that most of the things, and we will see, is like we can really approximate it as a power law distribution, and depending with different powers, like a power law index. Okay, so that's what the game we will play by changing the different particle energy distribution, because we don't know that. We have no idea about it. We will play with that and try to fit our actual observations with our models and try to see how they both fit. Okay. Right.
Uh, yeah, the next question is what could be the possible explanation for the origin of AGN jets?
Possible explanation origin of AGN jets. Well, I mean, we know jets exist. They have been detected hundreds of years ago. So people are trying to understand how these jets are essentially formed, and pretty much it's clear now with event horizon telescopes, and we are able to penetrate deeper and try to see how these jets form. So we really understand now that they are formed because of magnetic fields and this funnel shaped magnetic field structure that has been generated close to the black hole, driving the jets, which are known as Blanford snag jets. And then surrounding, you have a disk material which can also launch jets which are much slower, and they're called Bradford Payne jets. So there are different models, and pretty much we understand how these models are essentially functioning. But how the magnetic field comes, details are still a bit sketchy in that regard.
The next question is the formation of Asian knots is an open question. What might be its reason?
So there are two ways to form AGN knots due to in AGNs, right? So one is that you can have accretion flow which is intermittent, in the sense like it's not steady accretion, but accretion which is like accretion happening stops, happening stops, happening stops. So it's like breathing. So then your material also which has been pushed up goes in like a bullet fashion, like thak 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 thak. Okay, so there is a variability coming because of the accretion disk variability or this kind of thing. So you form knots. That is one way of explaining it. Second way is the jet itself becomes unstable. Okay, so you basically have all sorts of instability or magnetic processes that happens. I don't want to go in details. There are sausage modes, kink modes, several other modes are there, like which are unstable modes. And in those kind of situations, you also form knots. And therefore, you basically form knots because of an inherent instability or because of an external transient accretion fields.
Yeah, the next question is about Doppler shift. Will the jet beam will be blue shifted when it moves towards us?
Well, indeed, you basically have all these effects here. So that's as I rightly said here. So basically, if the jet is so this here you can see here on the left hand side, the arrow actually on the top is the relativistic Doppler boosting. So on the top, you see the arrow is pointing in the direction of the velocity direction with respect to the surrounding. So when you are going towards, you basically see everything kind of getting blue shifted. On the backwards is red shifted. So longitudinally, that's correct. But transversely, basically, it will just bend because of this angle cos theta. Okay, so there is an aspect that there is what you can say. Uh, um, uh, uh, you have a kind of you have this angular transverse effects, which kind of causes you boosting of the emission that is coming towards. So indeed, you can have motion. Your 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 flux gets boosted because of this effect here. So that is what you essentially see. Yes, you get flux boosted, and also the frequency changes. Yes.
Yeah. Next question put up is which type of parameter regarding black hole and galaxy we can predict from the jets? AGN
Which parameter? What parameter?
Which types of parameters probably they are asking regarding the black hole and galaxy we can predict from the jets?
Yes, very nice. So basically, by knowing the jet outflow or the velocity, we can essentially find out what is the accretion rate. If you know the accretion rate, we have some relations with accretion rate and mass. You can make an estimate of the mass. You can make an estimate of the spin. Many aspects of the galaxies can be informed from the jet physics itself. So many things can be done from jet physics.
Now the question is,
I think we should.
Yeah.
Maybe, do we really want to continue the questions? I don't mind answering all the questions.
One more question.
Okay.
Let us finish that. Sir, are the conditions you mentioned, like particle energy distribution, magnetic field, etc., applicable to both leptonic, hadronic in the same manner? How does it impact and affect both?
Well, you see, the point is very simple, right? You have a jet, you have a blob. This is our model, right? This is our model. It's a very simple model. I'm not saying that it is the best model that you can ever come up with. It's a simple model. So there are two aspects here. One is, what you can only get is the light, and you get an SED. Now you have points, as we will see. We have data points. You have for different energy or frequency, you have a data point. one data point of flux, two data point, and all these things. Now the point is that there are certain dynamical features, like the magnetic fields, the Lorentz factor, the size. These are all dynamical features or macroscopic features. But then there is also inside microscopic features. And as we will see, that by changing this, it significantly changes. And this is one of the exercise that I have also given to you. So this is something which you should do using AGN5 so that you can understand. You can answer your question by yourself only by doing this modeling so that you understand what happens when you change certain parameters. Okay, so definitely it plays a huge role. And there is, as you can see, there are a lot of parameters. Like we don't know the size, we don't know the Lorentz factor, many things, the particle distribution, magnetic fields, we don't know all of this. So right now, but we know what emission comes out from this. So now can we, by just looking at the emission, make a model which can fit this emission nicely? And that's the task that is basically given to you as part of this tutorial. So I would request now, if the chair permits, we can go towards.
There's one from audience. Last question that will be.
Excuse me, sir.
Please answer the question.
Yeah. Hello, sir.
Yes.
Yes.
When we say that the jets are forming, the role of magnetic field, the magnetic fields are solely from the accretion disks, or is there any other magnetic field that is also, playing any role, or only because of the accretion disk magnetic fields the jets are?
Basically, magnetic fields, as I told you, that there are some seed magnetic fields of the material which is get accreted. But closer to the accretion disk, you also generate magnetic fields by what is known as a dynamo mechanism. It is the same mechanism that happens pretty much in the center of our sun. Okay, so basically those kind of processes happen within the accretion disk. So you can have dynamo, you can have, so that's why you can amplify the fields, because you can have certain fields which will come, but you also have to amplify the fields because you need strong fields to drive. Remember one thing: the jets are magnetically dominated closer to the base of the flow. So your magnetic fields have to be stronger than your kinetic energy of the jet. And the jets have to start relativistically. It couldn't start non-relative. Right? So you have to ensure that you have strong magnetic fields at the base. And so several processes come into picture, including dynamo and MRI, so a magnetic rotational instability and so on. So these are all dynamo generation mechanisms.
Okay. Thank you, sir.
Okay. The questions are there, but shall we stop now or start?
I mean, I don't mind answering questions. I would be more than happy, but
one more
then we will
take.
not be able to cover the tutorials. That's
yes. But one more will take. That is special request is there. And that is, as the time grows, jets started floating around in the universe, very far away from the BH. Like if we ever come in to observe such things, can we tell that is the Asian jet left over?
Can the Asian jet? Can we tell if the Asian jet?
As time grows, jets started floating around in the universe, very far away from BH.
Yes.
Like if we ever come to observe such things, can we tell that it is the Asian jet left over?
Absolutely, absolutely. Very, very good question. I'm glad we took it as the last question. So this is basically what are known as the remnant AGNs, or essentially the old relic AGN relics. Okay. So here you can basically see, that's why I brought you out this M87. Now, this is a jet is there at the center, we know that. But if you see the structure at a very large scale, these are just leftover, which has been, because the jet is like not started now, it has started much earlier in time. And so all the material which has been pushed are now kind of emitting radio, very, very low frequency radio. So what happens is that this electron particle distribution cools down or loses energy and so on and so forth. And when you have very low energetic electrons, they will still produce synchrotron emission because you have magnetic fields. Weak magnetic fields, low energetic electrons still produce synchrotron emission. But then this emission will be in very low frequency radio. Now, if you are aware that India is basically part of one of the biggest consortium, which is known as the Square Kilometer Array. is, and that is square kilometer array is basically a array of antennas which is going to look at the sky in extremely low frequency radio wavelengths. And we expect that with SKA, we will be able to detect lots of such remnant radio galaxies or EGN jets, or what you can say, remnant radio galaxies or relic radio galaxies, because they will be the leftovers. They are like this gone away. So they are like completely, at a very, very large scale. So we will see how these structures, which are highly collimated, highly structured, closer to the black hole, how they get dissipated at much, much larger scales. So that is very, very, very crucial aspects that we can study with square kilometer array. And that is one of the science objectives also.
There are one more question on magnetohydrodynamics, and another is there is on experimental arrangement for measuring gravitational force of black hole. Is it possible?
Magnetohydrodynamics,
how do you create magnetohydrodynamic modeling of active galactic nuclei jets, as there are many sources of noise which makes the model difficult?
Absolutely. Absolutely. They make the model difficult, but you essentially also have to understand the macroscopical picture. And when you understand the macroscopical picture, like for example, the wiggling of these jets, the knots forming of these jets, you can explain very well with magnetohydrodynamics, the launching of these jets, how these jets are kind of thing. And there are several now advances coming in order to explain what you can say, the EHT emission. So people have been doing a suite of simulations and then trying to get the best fit to your EHT image. So they can explain what sort of accretion flow happens around it. So MHD modeling is the only way you can explain how this thing happens. So that is point number one. Now measuring the gravitational force, well, you have gravitational waves. Okay, so that is the only signature that you have when you want to understand binary black hole mergers, or essentially binary neutron star mergers. Now, many of the neutron star mergers also have an electromagnetic signature, so they can produce jets afterwards. But to measure the gravity of an isolated black hole, that is going to be a very tricky affair. So right now, binary merger black holes produce gravitational waves. We are very much detecting gravitational waves, and we can kind of understand what sort of gravity acts in this very nearby regions. So that's possible.
Thank you, sir. Over to Mahesh. Mahesh, please.
Yes, sir. So, are we going to go for the next part of this?
Yes, I think so. This overran much more than I expected. But what I wanted to do is, actually the best part is now that I have the tutorial, I just want to go through the tutorial, because if I can go through the tutorial, then everything else is kind of straightforward, and they can do this, and even attempt to do the tasks that are there. So if you permit, then
yeah. So you have already shared the material on the classroom. So now
yes, I have shared in the classroom,
screen, and you can share the screen and do the show some tutorial.
Exactly. So I'm going to do that. I'm going to do the tutorial. Okay. So I'm going to make it full screen. I request everyone to please download this thing. So I'm just going to remove this. So now that we have,
there were many messages. People had problem installing Sherpa.
Oh, I see. So we can then restrict not to use Sherpa right now. In this thing, I'm not using Sherpa. Then if there is any problem, but it's just does with pip install Sherpa, it should work. But depending on which version of Python they are using, but if they're using Python 3.10, I don't think it should be a big problem. So I would request everyone to upgrade their Python if possible. So that is also. Okay. New version, it's all asking to, it's asking to install Anaconda. Okay.
Is it possible to work on Google Colab and
It's
use
also possible, yeah.
AgentPy? Or, so
AgentPy
how
and
do we install AgentPy from Google Colab?
I think so. It should be not a big problem, but I can do that. But I just wanted to. I have this whole thing available that they can essentially use it here. But AgentPy does anyone having problem with AgentPy? AgentPy should not be a problem. AgentPy should not be a problem, guys. It's working fine in Colab. So Shweta, thank you. Gamma Pi, forget Gamma Pi. Gamma Pi, forget. Colab already has everything. Fantastic part. So that's great. So I'm happy that Colab has. Yeah. So yes, everyone should run if you want. Just in the first thing, exclamation pip install AgentPy and SharePy. This. So thank you, Shakib. You can basically have said this. Pip install AgentPy. It should install. And pip install this thing, right? So I think we have installed, if everyone has installed AgentPy, we can go ahead. Okay. So the first tutorial, which I have, we will only focus on leptonic emission. Now that you know what are leptonic emission and so on and so forth, there is also, it kind of makes our life easier because all these things is coded. Of course, ideally you would like to look at the equation and see and all these things, but we do not have time to go into the quantitative part. But I wanted you to have some play around with this package so that you can basically go back and do some more investigation and learn formulas, read formulas, and see how this kind of works. Okay, so let's begin. I hope everyone has installed AgentPy at least. For this, you don't need SharePy. For tutorial 1, you don't need SharePy at all. Okay, so let's start. We import, as you can see, we import basic NumPy and AstroPy and Matplotlib, some very simple basic functionality. AstroPy is important. I'm sure you have done an AstroPy notebook here. So that is there. And what is the learning outcome from here is to acquaint with the basic functionality of AgentPy, define various properties of this blob. You remember the one zone model I explained, that little blob, we'll kind of quantify that. And then quantify various properties of the blob from input parameters. Like if you give input parameters, how do you get other properties of the blob? Then we will obtain our first spectral linear distribution for a given set of parameters. And then how do you alter parameters and make full leptonic acid? Okay, so this is the task of the first tutorial. Okay, so this is what we will do. And now, the first we installed our nice NumPy, AstroPy, and so on and so forth. So that's why I've given the notebook itself so that I don't have to type. You can basically run it on their own to get an insight into what basically is happening. And we will go step by step. So if you are following this, then what I wanted to highlight here is that you have 5 things from AgentPy that you really require. One, defining the spectra. Remember, our blob has electrons, and we have to define a spectra, particle spectra of that electron. So that is one thing. So that is with AgentPy.spectra. You import, in this case, I'm defining as a power law. Then we have to define the properties of the blob, that is the emission region. So that's why from AgentPy.emission regions, import blob. Okay. Then, since we are doing leptonic, the low energy part, remember, is the synchrotron. So we define AgentPy.synchrotron and define the synchrotron, import the synchrotron library. And the high energy part was the Compton process. Basically, it's inverse Compton, but it's Compton process. So it's AgentPy.Compton, synchrotron self. So it's pretty simple. It's intuitive after you look at the lecture. And then there are some special plotting functions that these AgentPy provides to plot the spectral energy distribution and define some matplotlib RC params, which are essentially like what is the width of the lines, axis, font size, blah, blah. That's basic simple stuff. Okay. So that's what load MPL RC does. Okay. So that's it. So now we have installed this. Now there are two basic things. So the first is the basic functionality. Second is the AGN Pi functionality. Now our task starts. So the first task, define dynamical properties of the blob. Okay, so first we have to define our blob. So now we define the blob. So blob properties, what are the blob properties? You need to know the radius. But if you know the radius, it's a spherical object. Volume is straightforward. 4 pi by 3 pi r cubed. That's the volume of the blob. What distance is that blob? So where is the source? So in this case, I have used distance, which is basically from AstroPi. I think, yeah, AstroPi coordinates distance. And this is basically at 1 e to the power 27 centimeters. So that is very far away. It's about megaparsec scales, right? So 1 e to the power 27 is, I don't know, hundreds of megaparsec scales. Okay. So, and then you can convert it into Z. So that is the redshift of that particular source. This delta D is essentially nothing but, let me write here, it is 1 by gamma, okay, times 1 minus theta into cos of theta. Remember our Doppler factor. So this delta D is the Doppler factor. 1 over square root of 1 minus beta square into 1 minus beta. Now delta D is defined for frequency. So that's why 1 minus beta cos theta comes in the denominator and not on the numerator. In that formula, in the presentation, it is for the wavelength, but wavelength and frequency are inversely related. Okay. So this delta D is essentially defined as 1 by gamma, 1 minus beta cos theta. And beta is nothing but B by C. Okay. So, and then you also define gamma, which is 10. So if your gamma is 10 and delta is 10, then theta is very, very small, because for theta close to 0, this value will be theta, yeah. So this is basically like very small, and therefore you essentially get very small numbers. So we'll see how the theta comes, but that is how the theta is. So delta and theta is gamma, or it can be more also, I think. So, and then this is the magnetic field, which is defined as 1 Gauss. Okay. So this is how you define. These are the only properties which you require for the blob. Okay. You know the radius, volume is by default it comes. What distance is the blob? What is the Lorentz factor of the blob? So that is the gamma. And what is the Doppler? That means at what angle of inclination? Because if you have delta and gamma defined, you have your theta also defined. So that is like at what angle of inclination that blob is moving towards you, and you need magnetic fields. So these are the global parameters, so the macroscopic parameters of the blob that you can define like this. Okay, so it defines, right? Now, once the global parameters are defined, what we do is now we have to define what is inside this blob. As I told you, we are only worried about the electronic part, so we'll only define the electron spectra. We don't care about the proton spectra. We don't even know if the proton spectra has any role to play. And that is our assumption, because we are basically doing electronic spectra. So now, very simple. We know from standard integration, we can basically find out. So this is the total WE, the total non-thermal energy of electrons in ergs. And how do you do this? If I have a distribution of electrons, n gamma, or particle number density of particle, so n gamma d gamma is nothing but the number of electrons per unit volume within the band gamma and gamma plus d gamma. This is n gamma d gamma. Okay. Then what you do is you multiply it with the rest mass energy, the energy of the electron, that is MEC squared times gamma. So that is the energy of the electron. And then you integrate from a gamma min to gamma max. So you have defined some spectra. So that's, let's say, power law spectra from gamma min to gamma max. And you basically multiply it with volume. So then this whole units comes out to be in ergs, because integration is ergs per centimeter cube times the volume, that is essentially the ergs. So then what you need is you need to define the total energy in the electrons. You have to define the bounds, the gamma min and gamma max, and the nature. So in this case, we are taking power law, which is very simple. So how n gamma depends on this gamma. Now please remember, this is small gamma. It is the energy of the electron, okay, or the Lorentz factor of the electron. But this big gamma is the Lorentz factor of the blob. There are different things. This is called the bulk Lorentz factor. That is how the bulk flow is moving. And this is basically for the individual electron. What is the energy of that individual? The Lorentz factor of individual electron. Okay? And these gammas can be very large, 10 to the power 5, 10 to the power 6, depending on the energy of the electrons. Whereas this gamma can be of the order of 10, 15, 25, something like this. Okay? So that's a distinction between these two. Right? So now I define the total energy of the non-thermal particles to be 1e to the power 48 ergs. And then I can define using the power law function, which I have defined here. The power law AGN spectrum. Very simple, that we define what is the energy, what is the volume. And then this P is this power law index, which we define. So it's 2.8 I have chosen here. Gamma min, you can define it 1e to the power 2. So this is 100. Gamma max is 10 to the power 7. And the mass, because we are saying that it is the electron, so we are only focusing on the mass of the electron. Then, so anyone has a question? Where can I find this notebook? It is in the, Bharti, it is in the Google Drive, which I have shared. The link I've shared on the Google Classroom. Okay, what is the significance of beta? Basically, beta significance is that it is nothing but the velocity with which the material is flowing with respect to the speed of light. Okay, so gamma and beta are related. Okay, and so one can define a blob which is equal to blob which has the inputs RB, Z, delta T. So RB is basically the radius of the blob, the distance to the blob where it is. Delta D is the Doppler factor, gamma, B, and the distribution, which is inside it. So you run this, it runs fine, and everything is fine. So now we have defined our blob. Okay? So with all these input parameters, we have defined our blob. Now we can print the blob. So you can see now all the information has come of the blob. Radius of the blob is 10 to the power 16, exactly what we gave. Yes. Then you have a variability timescale. I come to this part later when we do this thing. We have a volume. We have redshift, which is 0.07. So at Z, 0.07. Okay, so it's about 100 megaparsec. Luminosity distance is 1e to the power 27. Doppler factor is 10. Gamma is 10. Beta and 0.995. So that is like highly relativistic. Theta, yes. So this is like 5 degrees. Now, by knowing the value of delta D and gamma, one can compute theta, which is the viewing angle. And that comes out to be 5.7 degrees. And B is the magnetic field, which is 1 Gauss. Coefficient of first order Fermi, forget about this. We are not accounting for any acceleration. So it's basically set to 1. So it doesn't play any role. So you can ignore this. The electron spectrum, we have a constant K. In general, there is a K factor here, which is the proportionality constant, which is here, 2.8, and this thing. And this K factor is obtained by using this equation. Because we have given omega WE, and N gamma is K gamma to the power minus P. So if you integrate this, you can get everything. And that K is basically coming here, 9.27 10 to the power 6 particles per centimeter. Okay. So this is all the information of the blob that we have. Okay. We can get more information of the blob. So you can get what is the total number of particles and total energy. So total energy we have given But total number of particles, there are about 5.44 10 to the power 51 electrons in that blob, if we give this particular spectrum. Okay. So that is about 10 to the power 51 electrons are essentially present in the blob. Then you can also, as we mentioned, as we were discussing about magnetically dominated, kinetically energy dominated, you can also compute the jet power of these things. So there are formulas to do this, and you can basically do this, which the blob does. You can see this is 10 to the power 44 ergs per second in particles. That means in kinetic energy, it's 10 to the power 44, and in magnetic energy, it's 10 to the power 43. So it's almost equivalent, just a factor of 2 or so. So I would say that this is kind of typical this, and the jet powers are also within the range of 10 to the power 42 to 46 of typically observed AGN jets. So they are highly powerful jets. 10 to the power 44, 10 to the power 44 ergs are very much in the range of the power. So now that we have defined our blob, we have done everything here. All the properties of the blob we know. So what we can do is now we can define the blob. Now we can basically do the emission coming out of this blob. So where I can find what is ME here? ME is the mass of the electron. Okay. Right. No, this cannot be done for the sun, for the jets of the sun as well. No, this is only done for AGN because it's AGN. All the formula is for the AGN jet. So that is mostly applicable for AGN jets. So now you can basically define synchrotron. We can, for the time being, comment on synchrotron SSA, because SSA is like self-absorption, which only happens at low energy. I have not gone in much details of this, but let us for the time being forget synchrotron SSA, and we can just comment on the SSA part. Okay, so now we have said, okay, let's then take this blob and let it emit synchrotron emission. So now we want to find out what is the flux that comes out from here. So we define a frequency band from, it's in log space. If you know NumPy log space, with 10 to the power 8 to 10 to the power 23 in hertz. And then for this synchrotron blob, we can find out the SED flux for the given frequency. Okay, so that is what this whole thing is doing, the sync SED, and then you are plotting the sync SED. Okay. So this is plot SED with the frequency on the x-axis and SED on the y-axis. We'll discuss the y-axis quantity. And on the axis, color is black and label is synchrotron. So let's plot this. Wonderful. What happened? Sync is not. Oh, I have not run this. Okay. Running here and running here. Okay, great. So you can clearly see a nice SED which is coming up. So it's basically like a hump-like feature. And remember, this is synchrotron. So this is the low energy part. Okay, this is not the full SED. We had seen 2 humps. This is the low energy part. So here you can see some variation here and some here, and this is covering this whole synchrotron part. Okay. Now, if you put synchrotron SA, incorporate this part, and then you plot the synchrotron SED. Okay, so you see the dashed line is synchrotron self-absorption. What you see is that there is some loss of energy, or SED is basically getting lesser here as compared to the normal synchrotron. And this is very, very typical of synchrotron self-absorption. So there is a physics behind absorbing of the photons that are basically ejected because of synchrotron, because of the high density of the electrons, and that is mainly in the very, very low energy, low frequency. So less than 10 to the power 8, 10 to the power 9 hertz. So there is a slight difference. But overall, if you look at higher frequency, it remains exactly the same. So it only affects the low frequency part. But this is also an important factor as far as synchrotron self-absorption. But what I wanted to show is that you can nicely see an SED being plotted. And what is important here is that there is this quantity here, which is nu F nu. Okay. So nu F nu quantity is basically in given as ergs per centimeter square per second. Yes. So, okay, self-synchrotron part again, I'll explain to it. So that is an ergs per centimeter square per second. Now this is nu F nu. And there is a reason why we plot in nu F nu. Because if you look at it, nu F nu, so F nu in general is given in units ergs per centimeter square per second per hertz. Okay, so that's the F nu, units of F nu. But when you multiply with nu, it's ergs per centimeter square per second, because there's a hertz factor goes away. But why you plot it in nu F nu? Because if you want to do a total energy coming out of this, okay, then you have to multiply with E, which is the energy of the photon, h nu. Okay, so F nu times h nu integration will give you the total energy. That's why you plotted nu F nu. So all SEDs are plotted with nu F nu, because then the integration under the area gives you an indication of how much energy that thing is emitting in that in this frequency band. So nu F nu gives you a much better understanding rather than F nu. F nu is will give you only a flux per frequency, but if you multiply with nu F nu, you get then it's a much more physical quantity to plot, because then you get a total energy from that HEN point. Okay. Now, what is our question? So there is some problem. What is the problem here? Module not found. What is the problem? Module. Which module is not found? I don't understand what module is not found. But okay, I think someone can help him in that way. But what should we define blob in as in the code? If someone can ask me this better, I don't understand. Okay, I'm lost here. I mean, so many questions here. Can someone ask on speaker? I can speak up and ask.
Okay, I'll keep a tab.
Yeah. Okay. Right. So basically, what you get here is a synchrotron absorption, but forget about the self-absorption. So self-absorption is a feature which you get because the photon that is coming out from the synchrotron process gets absorbed because of high density of electrons present there. So that gets absorbed and that does not come out. But this only happens at the low frequency photons only. Only low frequency photons gets absorbed. That is, the electrons itself are also absorbing the photons. That is also possible, but only at a very low frequency. Okay, this is synchrotron self-absorption. And then the idea is that, okay, now that we have defined for synchrotron, it is one section of the hump. We can do the same thing for synchrotron self-Compton, but since we have defined the blob, we don't have to define the blob again. It's simple. We define the emission, that is SSC synchrotron self-Compton blob. And then if you want the self-absorption also, it is possible. You do this. And again, just the same way, you can plot this and you will get the SED. So now you can see here that this SED ranges from 10 to power 16, 10 to power 16 to basically 10 to power 28. So this is the high energy band. And this one was going up to 10 to power 23. Okay, so 10 to the power 23 and 10 to the power 16. So this is like, if you plot this together, you will get a complete SED. And that is essentially one of the tasks that I have given here, and which can be basically done with the same blob. You don't have to change the blob. The only thing that you have to change in this particular aspect is that all the properties of blob remain the same, but what is required is that You need to, if you look at the plot, if I basically see the image, this is the image that you have to reproduce. This is the image from our textbook, which has been done for this blob. Okay, but here you can see that there is a solid line which is with gamma 2 or gamma max to be 10 to the power 7, which we have done. I think we have taken 10 to the power 7, right? Gamma max was 10 to the power 7 for us. Yes, gamma max was 10 to the power 7. What I want is you can define another blob 2, which basically has a different gamma max, which is 10 to the power 5. And then you can plot all the spectrum together. And then you would basically be able to produce the textbook like figure in your Python. So this is something we can do, and this I leave it up as a task. We can follow the same ideology, which is basically given here, and that can help you to do this. But you have to define a blob 2. So you have to define blob 2. So we can define any 2 or something like this. So we can copy this at another time, another place. Okay, so this is like this. But here you can define any 2, blob 2, any 2. This is 10 to the power 5, right? That is the idea. So now you define blob 2. Then you define sync 2 is equal to sync proton blob 2. And SSC2 is equal to synchrotron self-Compton blob 2, right? Then you can basically define the figure and axis. Just copy paste. So we can define slightly bigger figure. So let us make it 12 and 6. And blob 2 ho gaya. So then you can do new. This we have defined as new synchrotron, new SYN. Okay, new SYN. SCD. SCD sync, right? A sync SCD. Then this is 1E7, 1E7, 7. We can do this. Okay. So now you can see both the SEDs are plotted together over here. 1E7, 1E7. Okay. So that is fine. And then you can also define for the second one, which is you can define for this one sync SED2 is equal to, the way we have defined it here is, yeah, so SED flux. Sync SED2 is equal to sync 2 dot SED flux. This will be new. Then SSC SED2 is equal to SSC2 dot SED flux. New. Okay. And then you can just plot this. Let's plot this red, then 5, Very nice. Carbon, SCD. Oh. Why is not defined? SSP? No. Right. So now you can also volume. Now you can see. So now this is exactly like the same thing over here. And this is how you can basically make an SED. Okay, so you have this two SED over here, and the red one is basically for 1E5, and this thing is for. Okay, so I think many of you people are still working on getting this installed and so on. So I think it's very difficult, but I think what the intention is that to have these models there, and I think the documentation of AGNPy is also pretty robust. So you can basically follow this. So my intention over here in this tutorial was to explain to you how this SED is being done. And all this thing is, if you have been following, this is where you can basically do a lot of stuff. And in the next part, which I wanted to cover, actually had the real observational data and then the fitting associated with it. But I don't know whether we will be able to take that up as such. But what I wanted you for the tasks, because now that this part is done for this initial part was the assignment, I wanted to check for yourself how the SEDs change with the change in the following quantities. Let's say you change the magnetic fields to, let's say, 0.10⁻⁵ Gauss or something like this. How will the SED change? If you change the power law, let's say from 2.8 to, let's say, 3.4, how the power law index, how the SED will change. Okay, so there are so many things one can do and essentially study this particular SED evolution by just modeling. But this modeling is only to give you an insight on how different parameters behave or affect the SED. What is more important is that you want to compare this modeling with observations. Okay, so in the next part, which is the case study, if you, I think what I'm going to do is this is also available. I'm just going to run it so that you can basically see how the data is done.
You can,
yeah,
you can extend the session if your time permits.
Yeah, I can extend the session. I mean to say,
yeah.
I can definitely extend the session for another half an hour because this will require only half an hour for me to do because everything is the same.
Sure.
Everything is the same. I don't mind extending the session to another half an hour if everyone is willing to do it. But are people able to get it? Is there anyone who is able to get this part? At least get the plot for these things without any issues?
Yes, sir, because
you have got it. Okay. I'll say, so that is good. So at least some people have got it. So that's great. So yes, it works. Okay. And I hope that everyone has understood. So maybe we can take some questions before we go to the tutorial. And I would request people who have got this to try playing with other parameters as assignment tasks. That how do magnetic fields affects, how this key parameter affects. So you have all the ball games that is there. My intention was that if I change one parameter, how do you do this full analysis and get the full SED? So this is what I showed here. And now you can play and do all sorts of things by changing different parameters. But what is interesting now is that when in this case study part, we have actual data. Okay, so it's not, we will not be able to do, we'll change P and then do all the runs, then we change B and do all the runs, because there's so many parameters and so many things. It's extremely difficult to kind of manually do this. Okay, so that's why you need something called as hyperparameter fitting. So like if you have multiple parameters, you can do multiple parameter runs and find the best set of parameters that fits the observation. Okay, so that's the task for the next part, and this is what we really actually do. When we have an actual data, we plot the data with uncertainties, and then we try to kind of fit our SED model to this. Okay, and then we try to understand what best fit parameters takes place, and you can actually have an insight into what are the power, the jet power, and so on for the best fit parameters. So that is the task which I wanted to do for the case study. Okay, so people who have done this, they can already go ahead with the case study because it is very straightforward. There's only one concept that I have to teach you. But before I go there, is there anyone has any questions here apart from not getting the AGN file installed and so on? Is there anyone with questions?
They are asking question. They are asking, explain the assignment part once again briefly.
Okay, let's do this then. Okay, I'll do one quick run. Okay, fine, for the benefit of everyone. Okay, so this assignment, if you look at it, it has, the idea was to give you an insight on how do you define a blob, how do you define the particle spectra inside the blob, and then with that blob being defined, how do you plot the spectral energy distribution, assuming it's a full leptonic model. Okay, so that's the idea of this exercise. What we did was, initially we started by defining some very simple standard libraries like NumPy, AstroPy, Matplotlib, and so on. So this is standard stuff. And in AGNPy, we focused on 5 essential routines. One was for the spectra, like how do you define the spectra of the particles? So that is a module associated with it. Then how do you define the blob, the microparameters of the blob like magnetic field and so on. So there is a module associated with the emission regions. Then there is a module associated with synchrotron. So it computes the synchrotron emissivity and the flux associated with it. And there is a module associated with synchrotron self-count. So that is like the inverse Compton process that we say. So it computes that emissivity. These are the two synchrotron and synchrotron self-countable. It basically does the whole sorts of algebra. And then finally plotting. So this is for defining the blob. This is defining inside the blob. This is to define the emission in synchrotron and synchrotron self-countable. And finally plotting. So these are the 5 things that we extract or import from AGNPy, and we basically do the plotting. Now, to define the blob, you define the radius, volume, distance, Doppler factor of the blob, the gamma, and the magnetic field, which is in Gauss. So all of this are macro parameters, outer part, blob itself. And then you have basically to define what is inside the blob. So for that, you have to define the energy distribution inside the blob. So for the energy distribution inside the blob, you need to define how the electrons are distributed in gamma space, small gamma, and from what gamma min to what gamma max, and what is the total energy of this. So with this information, with just this information, you can uniquely define how the spectra will be inside this region. And our assumption is that it has a power law spectrum from 100 gamma to gamma max equal to 10 to the power 7. Now, someone asked, why did you multiply it with the total energy? So it's rest mass energy times gamma. That's the total energy. That's the energy of the electron times the number density of the electrons spread, the distribution or number density of it. So that's the total energy of the electrons per unit volume. If you multiply with volume, that is the total energy in electrons which you want to give as an input, which is 10 to the power 48. And gamma max and gamma min are to be defined, and P, the slope of the power loss spectra, has to be defined. Okay, and that's it. And then you define your blob. That is how you define your blob, by combining the power law spectra that you have used and the macroscopic properties that you have used. Once the blob is defined, you can print the blob and see all the properties of the blob. You can also get other properties of the blob like power of jet, magnetic field of the jet, because everything is computed. Then you define the synchrotron property of the blob. So you compute here all the synchrotron emission, emissivities, and so on for the blob that is in there. And then you basically use that to compute the SE. Okay, so that's for a given range of frequency, because you want to plot that SE. And then finally you plot that. So that's this black line, black solid line. And the dashed line includes synchrotron self-absorption, but that's a much more detailed thing. And I just wanted to show it's very easy to include synchrotron self-absorption by just putting SSA equal to 2. Okay. And similarly, you can do the same way with the same blob. Like you define synchrotron, you can define SSC, synchrotron self-Compton, and then you can also have synchrotron self-Compton as blob associated with it. And then you can plot them. So you get this basic sole feature over here. And then, as I told you, you can make this plot here by changing gamma max. And that's what we did here. We defined another blob 2. Everything else was same, but our gamma max was changed. Here it is 10 to the power 5. And remember, here it was 10 to the power 7 gamma max. Okay. So everything changed here. And then you can basically make the plot here. Remember, I had to put a Y limit. So because I wanted to match directly with the textbook figure. So that's what I did. And this goes up to 10 to the power 30. That's it. And then you get the plot, which is very similar to the textbook. That's the idea behind this. Any more questions?
Shall I run a small quick poll?
Yes.
Yeah, and then of course we can continue with this, but this will be maybe for 2 minutes or so.
Okay.
So all participants, please respond to the poll. I have launched it. I will end the poll in 15 seconds. Okay, ending the poll now. Yeah. Thank you, Bhargav.
Thank you,
You can
everyone.
continue.
Yeah, thank you so much for the poll. And as I can see that many of you have liked the lecture, which I really like. But the tutorial, many of you could do it in parallel, about 30% or so. Whereas the other, more than 50% wanted to focus and work on the tutorial later. And I really appreciate that you can work on the tutorial later. For people who have struggled, I think I can understand that it's a bit uh, intensive, but if you basically look at it afterwards, I think you can get a better idea on what this is all about. And that is the whole idea behind this. Okay, so let's, now that we know how to do the blob definition, we can go a little bit more quicker in the case study, which is where we want to kind of really use the data to fit it. Okay, so that's the idea. Now, this only people who have been able to install Sherpa can do this, because that is the it requires Sherpa now. So that's the idea. So now let's basically start. So again, the basic idea is first you have to define the blob. Once the blob is defined, we can basically define our synchrotron and synchrotron self-component, because for this source, we're going to assume only leptonic model. So that is there. So now here there are additional inputs. So these are standard from what you had earlier. Only difference is that now we are going to use a broken power law. Broken power law is power law to certain extent, and then with another power law, P1 and P2, which is basically given by this form. So this is how you define your spectra. And then everything else is same. You have additional thing, which is the fit, because you will have to now fit the observation data. So that basically fit is there. And everything else is same. And also this fitting procedure comes for the statistics and optimization methods of Sherpa. So Sherpa is an optimizer, hyperparameter optimization method. I will not go into details of this. Fairly used library, not kind of new. People have been using this, but it's just machine learning approach to kind of make a better fit to this. So we're just gonna load this. So that's fine. And then we do the same thing now. Remember now, our blob is slightly, we don't need to define the blob explicitly, but we will define the K, which is essentially the normalization constant. P1 and P2 are those P1 and P2 because there are two powers of your spectra. N gamma is basically this. Gamma B is the break, this thing. This is this gamma B. So, and this is a Heaviside function. So this is either 0 or 1, depending on whether gamma min is greater than gamma B or less than gamma B. Or gamma B is greater than gamma min, and so on and so forth. And then there's a gamma min and a gamma max. Okay. So, okay, so that's something is going on over there. So we'll define the synchrotron self-component model. Now, this is a very interesting. So here, now we are defining a model and not the itself. So essentially, with backend Sherpa, you can define the model, and then inside the model, what you have to do is you can give all the other parameters like Z, what Z. So these are, so once you define a model is basically, so if I can essentially, maybe you can, so here you can see, if I just define this model, synchronous self-component NE backend Sherpa, then, and I just print this, so just write SSC model and this, then it says nothing is evaluated, but only gamma min is given, and there is like a range associated with it. So there's a range associated with it, and some default value it has been taken. This is fine. It is taking these values and so on and so forth. But otherwise, it's very default value like gamma min, gamma max. All these values it's taking. There's a min and a max associated with it. So this is like a range in which this will be varied. The P1 has a range, P2 has a range, gamma B has a range. So this is like the break gamma, the minimum gamma, and so on. But all of this are given by default. Some random value is given by default, which you can change. Okay, so then you can add, and there is a range associated with it. So 0.01 and 10 and so on and so forth. And then you have the model, this thing. Sir, it didn't show for me. Okay. No, it's basically if you type SSC model, it should come. Synchronous self-confident SSC model, it will come if the Sherpa is properly done. Okay. So then there will be, otherwise there will be a problem. So then you can, by observational values, you can put some values here. And here there is an important parameter which is called the T variable. So that is like the variability timescales. So usually these AGN jets, these blobs are basically variable. So in the sense like they emit and then after certain times they have a stark variability. So emission basically is variable, and you can compute and you can basically study that blob for a very long time and find out that variability timescale. And this variability timescale is associated or related to the size of the blob based on causality conditions. So this is the formula which relates the size of the blob with variability timescales. And variability timescale is an observable. So you can observe that variability timescale. You can essentially, you know the Z, you know the delta D, because sometimes you know the line of sight angle and so on. So you can give some initial guesses for these things, and then you update this SSC model. So now if you give the SSC model again, all these things will be updated. So initially it was 0.1, by default it took it. Now it is 0.038 because that's what you give. Then delta D was 18, by default it was 10. So it has now changed to 18. Log 10B, that is basically the value of magnetic field. Log 10 of the magnetic field, that value is there and is there. And then the variability time scale, which is 1 day in seconds, which is 86400 seconds. And then there are these ranges. So there's a range for which the Sherpa will kind of change the parameters, because doing this by hand is crazy. You have 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters. Even though there are 10, there is one important point which I've made here, which is freeze the SSC model T bar, which is now T bar has to be fixed to that, because this is an observable. Observe. I have observed this. I cannot change this. I don't want you to vary this. I want to be freezed to this value. Okay, because this is real observation. Okay, so I've taken this observation, and now this is my model. This is my model that I have to end up with. And then, of course, I have data points. If you look at the data, there is in the folder itself. If you look at the folder, there is data folder. Inside data folder, there is Merkinian 421 2011, and 2011 there's a CSV file. You can basically see that it has all the information regarding the flux and so on. So if I can open it, so you can see EE-CSV file is a CSV file only, but with some header. So here you basically see the frequency, you see the flux, and then there are essentially some other quantities which is written here. So it will be there. So this is flux, and then data type. This is error in frequency. This is error in frequency, and this is error in flux. So that is basically this thing, and then you have the telescope with which it has been taken. So that is like a data instrument type. So RATAN, VLBA, and so on and so forth. So errors and everything are kind of there in this data, and everything is basically can be used to get this. So redshift is given, period is given, everything is given here. So now for each instrument, usually you have a systematics associated with it. So basically each instrument has some instrumentation systematics, and that is basically also given to you. So now what you have to do is you have to basically use this systematics to compute the errors. And what I've done here is E-min is basically, now I want to plot it from 10 to power 11 hertz to 100 tera electron volts. That's my range from where I want to plot my data. And this is my path to the SED. So that's my data path, where your data folder is. And then what I'm going to do is I'm going to define an SED, which is with load Sherpa flux points with SED points, SED path from E-min, Emax, and using this systematic directive. So now this SED, what load Sherpa flux points does is it will read that data and it will basically compute the error and everything and everything. And then you can plot this. So now if you do this, and remember this is the plot up to, so let me just comment this and then we can just plot it. Okay, so then we just need AX dot set X scale to be log and AX dot set Y scale to be log. Oh, I didn't run this. Okay, I didn't run this. Okay, I ran this. Then, right. So this is the data. Okay. So now you basically see this is the data. You can clearly see now it has a 2-hump structure, which is what you expect from an AGN jet. You have error bar associated with it, which we have plot here. AX error bar, SED.X, SED.Y, Y error is there, get error marker, and this thing. And this is basically from a paper which is Abdo 2011. So this is actually the data, the real data. And this is really, it looks like this, basically. So now your job is that you have given a model. Okay, here is your model, SSC model. You want to check whether your model will be fitting, overfitting with this data. So what you do is you just plot that model. And you see this is the thing. Now, it is clear that the model that you have chosen is definitely not fitting the data. Because here you see that the data is much above, also over here, and especially in the higher energy band, it's all gone. Whether the model that you have is much smaller or lower, is predicting at least factor of 5 or 10 lower than what you basically is actually the data. Okay. So now what we have to do is we will run the Sherpa routine, which will iterate in this whole range of all these parameters and find us the best fit parameter for the model that to be fitted. Okay. So now this is our task. Our model, we chose some randomly these numbers. This is observed 0.038. This was random. This is observed. So this is fine. This is random. Some initial choices we gave and some range we gave. And now what we need is we need to kind of fit this. So what we do is we kind of define a fitter, which is Sherpa fit, which uses the SED. Remember, SED is our data, SST is our model, and it has some statistics. There is chi-square statistics, and it uses some optimization method, which is known as Levenberg-Marquardt method. So these are some technical terms. You can go in details to see this, but this is all kind of put in there. Okay, and then you can basically get the best fit from the fitter. So you try to fit this and see if the fit is successful or not. So if I run this, it will take about 10 to 12 seconds or up to 20 or 30 seconds, depending on your processor, and it will point out certain things. Right. So mine took about 11 seconds. And the fit successful? Yes, it was successful. The method was Levenberg, statistics chi-square. Here are all the statistics parameter. And then finally, it gives you the best fit for K, P1, P2, log 10 gamma B, the break, delta, and beta. Remember, T bar, it was frozen. For us, the T bar was frozen to 1 day. But now the new parameter is this. So now with this new parameter, we can again plot this. Now our new SSE model has been updated. So if you want it, we can insert cell above. So now you can do SSE model. SSE model has the best fit parameter, 7.88461. Before, you remember, it was what values we put. So these were random values we put, some initial guesses, and now these are best fit parameters that comes here. And you basically get this. And then if I now plot this SSE model, and voila, it fits very well to the data. Okay, so that's how you basically do this. And the beauty is that with this SSE model, now with all this information that you have, you can reconstruct all the properties of the jet, because now you have everything. So you can create a blob which is basically there with this best fit parameters. You can create a blob with this best fit parameters, and then you can basically find out its jet energy, its magnetic energy, and try to answer these questions. For example, Markinian 421, which is the data of this thing, it's a blazar. It's a PLX kind of blazar, and so therefore the jet basically has it's almost along the line of sight is almost zero, and Lorentz factor you can assume it to be like Lorentz factor at delta D. So this delta T is about 19.8. You can assume gamma to be also of the order of 19.8. Then you can define your blob, and from the best model you can estimate the jet kinetic and the jet magnetic power. And you will see that this value comes out to be of the order of 10 to the power 44 ounce per second, which is also kind of making sense. Then next part would be that can you attempt to fit the same data with the power law distribution, not with the broken power law, but with the power law distribution. So if you change the power to change it to power law, instead of a broken power, change it to power law, what happens? Can you obtain a best fit thing? And will the power estimated from there be consistent with what is the actual power? So these kind of things one has to check. And then there is also another data I have given, which is of PKS 1510. And there it's a slightly different model fits in, but can you try to fit the leptonic model over? Then what happens? So these are the things which you can try as part of this exercise. Okay. Yeah, it's getting too much complex. Yeah, exactly. So that's why that's nice. So so I think that is why I wanted, because this is really going complex. So what we can do is we can stop here, and we can, I would request the organizers to can go into more detail of this thing and then explain them how this is done, because this is really the state of the art, what people do to do the modeling of SED. So my intention was to give you an insight of how people actually do this kind of. So it's a black box right now, but if you use this, I think you get a lot of insights into how this happens. So I'll stop here, and I would thank for the patience for everyone. And I hope if you have any questions, you can always come and write to me. I'll be more than happy to answer. And if you're interested to do more research into this, and if you're master students, always welcome to apply for PhD positions. I have some PhD positions also open coming this fall. Okay. So thank you, everyone. And thanks for all the patience and support. Thank you.
Thank you. On behalf of Wilson College and IIPT Mumbai SRC 08B and Krittika team, I thank today's speaker, Dr. Bhargav Vaidya. He beautifully explained the tutorial problems also, as well as the theoretical aspect behind that. And what is needed is the statistical models. You try to understand the meaning and the purpose of the statistical models, and apply certain physics principles. That will be very good to continue your study in this particular branch. Friends, continue with your practice. It is just the beginning, but you can supposed to carry out a lot of practical aspects practice more for this particular course and learn more and more about this. Thank you, sir, once again.
Thank you, sir. Thank you so much for your time and effort and inviting me for this very nice winter school. I hope I was able to help students to learn and at least interest them in this.
Yes,
And
thank you.
with this,
It was really very interesting topic, and you
Very,
really
I
made
mean,
it lucid. Uh,
thank
so
you. Thank you
yeah,
so much.
that
Yeah.
is something really great.